Hey, welcome back. I have a question for you. How do you use Patterson and Hennessy textbook to figure out if an egg is hard-boiled or not? You take the book, use it as a flat surface, and spin an egg on it. When you stop the spinning, whether it wiggles or not determines whether the egg is hard-boiled. In this case, it's most likely hard-boiled. But we're still talking about RISC-V instruction set architecture and assembly instructions. We've learned 3 instructions so far: add, sub, and add immediate. The book and the green sheet uses a very compact description to very compactly remind you what these instructions do. It is in a language called Verilog. We are not learning Verilog in this class, but it is a language that in syntax is very similar to C, although it does completely different stuff. It is used for describing hardware. But given its simple syntax similar to C, we can infer what each instruction does from its compact description. For example, the add instruction adds the contents of the register RS2 to the contents of a register RS1 and stores it in the destination register RD. Conversely, the sub instruction takes the contents of a source register RS2, subtracts it from the source register RS1, from the contents of a source register RS1, and stores the result in the destination register RD. Our add immediate instruction is similar, but a little bit different. It takes the contents of the source register RS1 and adds an immediate value to it. Immediate value is a constant that is encoded as a part of an instruction. So it is there in the instruction. The processor takes that number from the instruction and adds it to the contents of a register RS1 and stores the result in the destination register RD. There is a limited number of registers in every processor. RISC-V architecture specifies 32 registers, out of which we can theoretically use up to 31 because register X0 is hardwired to 0, so we can use up to 31 of them for storing temporary variables in them. But what we'll find out, some of these registers in more complex programs have some designated use for something else. So we generally will be able to use less than 30 registers. Registers are scarce, so it's important to be cautious on how we use them. We want our programs to be fairly compact, and we would like to reuse registers as to store temporary variables. So for example, in the previous segment, the last example that I've done, you might have seen that we could have used one less register to store temporary values. In general, it is a job of an optimizing compiler to minimize the register usage. When we are done with an optimization, what we'll find out is that we have to use for a particular computational routine or for a compute kernel, we have to use a certain number of registers. That number of registers is called the register footprint for a particular kernel. But we have already seen that we work with larger amounts of data. So we'll have to spill out of the registers and spill over to memory. So it's important to understand how does the memory work with the processor. We have seen this picture before. It is a picture that will so frequently appear in this class that it is well worth remembering. Perhaps getting a tattoo or a temporary tattoo till the end of the semester until it gets completely engraved in our memory. On the left-hand side, we have a processor connected to the memory, and there is input and the output. We're going to focus for now on the processor and the memory. Processor has its data path with the registers and ALU inside of it, and the memory is there. Memory stores our program and the data that we work on. Memory can be viewed as a large one-dimensional array with the address acting as the index to that array, starting at 0. To access a word in memory, processor must supply an address. An address is right here. And we are going to use a little different color for that. Address is there. So address is calculated by a processor and is used to point to a particular word in the memory. The address is typically specified as an offset to a base pointer. So each data array that is laid out in the memory will have its base pointer, and when we would like to access a particular element in that array, we will have to calculate an offset with respect to that base pointer. There are two operations that we would like to do when we point to a particular word in a memory. We can read or we can write. It's really important to remember the direction of these two operations. We always load from and store to the memory. The world is processor-centric. All the main action happens inside the processor, and the memory is just out there. So when we are writing data, we are storing to the memory. So remember this, store to memory, because it'll help us really. If you ever get confused with the instructions, what do? Store to the memory is going to help a lot. Similarly, when we are reading from the memory into the processor. So load from memory has a direction from the memory into the processor. Store to has an arrow pointing from the processor to the memory. The other thing that is important to remember is the layout of the data in the memory. Memory is organized into words, and words in RISC-V that we are studying in this class are 32 bits wide. They nicely match the register widths that we have in our processor. So the data that is stored in a register nicely fits in each memory word. But keep in mind that we frequently like to work with something that is shorter than 32 bits, like characters or values of colors in our images. They are 8 bits. So we have to have an efficient way of putting together 4 bytes into a word such that we don't occupy too much space with unnecessary space with zeros. Each word of 32 bits will fit 4 bytes, 8 bits each. So when we store bytes in words in memory, which way do they go? In RISC-V architecture, they follow a particular convention that has a funny name called little endian. What does that mean? That means that the least significant byte in a word, this one over here, gets the smallest address inside that word. So fits into the bits 0 to 7 in a word. It could have been done the other way, it would have been called differently, but it follows in RISC-V the little endian convention. So essentially the least significant byte gets the lowest byte address, then goes to the next one, and so on, moving to the left. And then the next address comes around, and we continue serpentining through the memory array. Words have their addresses, they inherit them basically from the bytes. So this would be a word with an address 0, this word would have an address 4, and this word would have an address 8, and this would have an address 12. So essentially, word address is the same as the address of rightmost byte, its least significant byte. Okay, Hopefully this was clear. To make it even more clear, let's understand different options how data can be written in the memory. We follow this convention of endianness, and endianness has, kind of it's a funny word. It computer scientists have associated with a novel from the 18th century, from 1726, written by an Irish writer, Jonathan Swift, named Gulliver's Travels. And in his travels, Gulliver encounters an imaginary society where there is an interesting rift going on, where there is basically a political issue. Should the eggs be broken, hard-boiled eggs should be broken little side or the big side? So the people who break the eggs on the little side are called little endians, and the people who break the eggs big side first are the big endians. It's a kind of an interesting dispute. Sounds silly until we see what kind of these political disputes we have in 21st century. But going back to RISC-V and instruction set architectures, RISC-V, hopefully you'll remember forever, is a little endian, follows the little endian convention. So RISC-V always breaks the end from the little side. There are big endian architectures out there, but let's make sure that we understand the main difference between them. Now, endianness governs only the order of how bytes are stored in memory. Bits are always stored the same way. The least significant bit goes at the lowest bit position, right there. So if you would like to write C2, the more significant nibble, 1001, always goes in the upper position in the byte, and the less significant nibble, 0010, goes in the is positioned in the lower bits. Now, when we talk about the endianness, this is about storing the bytes. So if we would like to write the number 1025, which easily decomposes to 1024 plus 1, we need to write 4 bytes. The first 2 bytes are zeros, and byte 1 would have 00000100. The byte 0 would store a value of all zeros and 1 at the end. In little endian convention, byte 0 is placed in the address 0, the least significant address. Byte 1 goes to the address 1, byte 2 to address 2, and byte 3 to address 3. And that's it. Big endian convention stores byte 0 in address 3, byte 1 in address 2, byte 2 in address 1, and byte 3 in address 0. Majority of this world follows little endian convention. Majority of processors out there, maybe 90%, are little endian. But some important ones follow the big endian convention, like IBM's Big Iron servers, and some of the microcontrollers, and a lot of automotive processors. But this is not just, endianness is not just the matter of processor architectures. It exists in the real world. For example, my name in majority of the world and in the US is written as Borivoje Nikolic. My first name first, then my last name goes second. If I were to write it in China or in Hungary and some other places, Finland I think follows that as well, it would be my surname first and then followed by my first name. Java packages follow kind of a big endian convention. Internet addresses, internet names follow little endian convention. One interesting thing are the dates. So there is an international standard, ISO standard 8601, that specifies how the dates should be written as first, 4-digit years followed by 2-digit months and 2-digit days. And that's a big endian way of writing dates, and that's really convenient when you try to, that's how I save everything in my computer, because it's very easy way to figure out which pictures are, come first, how to order the pictures in time. When I write them in European way, it would come as days first, months second, and year last. A little harder to sort it that way. But the US way is middle endian or mid-endian. We first write the months, then the days, then the years. Don't ask me why. Hard to understand that. Like some other things, not easy to understand. Anyway, there are other examples of big endian, of people who eat the crust first in a pizza. The people who eat the thin part of the pizza first would be considered little endians. And there are many other examples like that. We'll break here. We'll come back to talk about actual load and store instructions that work with the memory. See you there.